Good evening, everyone. Okay, today I will give you another example problem for the revised simplex method. Okay? And we've learned that unlike the ordinary simplex method, revised simplex method updates small portion of the table at each iteration, right? So eventually we could save lots of time and effort compared to the ordinary simplex method. And I want you to keep in mind that if you have original matrix, original table, and the basis inverse matrix, and the basis set, then you are able to compute any part of the current table corresponding to the basis set, right? This is the basis of the revised simplex algorithm. And I almost forgot last time while I was solving the example number 2, I made a mistake. I think at iteration number 2. So let me go over iteration number 2 again. Let's say we've started iteration number 2 with this initial table and the basis set B was 4, 5, 1. The new basis inverse matrix A superscript B -1 is 3 by 3 matrix, right? 1, 0, 0, 0, 1, 0, -4, -2, and 0.5, right? Okay, so we have started iteration number 2 with this 3 information, right? And the simplex multiplier vector, which is represented by pi, has been obtained 0, 0, 30, right? And because we are dealing with maximization problem, and the non-basic variable x3 is the only variable which has the positive relative profit, which means x3 must enter the basis, right? Variable. And the substitution rate, which is the new constraint coefficient corresponding to this entering variable, which is represented by alpha, has been obtained as -1.5 and 0.25, right? Actually, there is a transpose. The alpha was like this. Which means the alpha values goes to here, right? -1.5, 0.25. And then right now we need to perform the minimum ratio test. So we need to compute the right-hand side values for the current table. That is represented by beta, right? Beta was 16.44, right? So we can update the current table 1644, right? And the minimum ratio tells us the second ratio, which is this, is the minimum. So x3 variable must enter the basis in this row, right? Which means currently the basis is 451. So the second base variable number x5 will be replaced by the entering variable, right? So the new basis becomes 431 instead of 451, right? That's what we've done last time. And because the new basis is 431, new basis matrix becomes, using the original table, 4, 3, 1, right? The new basis matrix becomes 1, 0, 0, 1, 1.5, 0.5, and A, 4, 2. Is that correct? Because the basis matrix is obtained by taking the basic variable columns of the constraint coefficient, right? And okay, and now we need to update the basis inverse matrix, right? Which means we need to get new basis inverse matrix, which should be another 3 by 3 matrix, right? And we've learned the new basis matrix, basis inverse matrix, can be obtained by updating the old inverse matrix with the pivot column, right? So what we've done is write down the basis inverse matrix, that is the old one, right? And then the alpha right here. So this is the pivot column, right? And so the old basis inverse matrix is this, right? 1, 0, 0, 0, 1, 0, negative 4, negative 2, 0.5. And alpha is negative 1, 0.5, 0.25, right? And this is where I made a mistake last time. I've used constraint coefficient vector for x3 variable from the original table. However, I should have to use this value, okay? And this made a big difference last time. And using the elementary row operations, we can make this part to 0, 1, 0, right? And using XR, this can be done so easily. So I put all the values for old basis inverse matrix, 1, 0, negative 4, 0, 1, negative 2, 0, 0, 0.5, negative 1, negative 2, no, 0.5, 0.25. Is that correct? So this is the pivot column, right? And this is the pivot row, which means this becomes the pivot cell, right? And in the next iteration, we need to make this part to 0, 1, 0, right? So first of all, we need to make 1 from 0.5. So the second row must be multiplied by 2, right? Times 2. And the third row will be replaced by third row minus this times 0.25 divided by 0.5. Okay. The first row will be replaced by the first row plus second row times 2, right? And then copy the formula and paste it. Now, this part provides the new basis inverse matrix, right? So, we have a new basis set. B is 3, 4, 3, 1. And the new basis inverse matrix, which is 1, 0, 0, 2, 2, negative 0.5, negative A, negative 4, 1.5, right? Now, again, we have initial table, new basis set, the new basis inverse matrix. So we are able to begin the next iteration, the iteration number 3, right? Again, the first step is to compute the simplex multiplier vector pi, right? Which is represented by CB times basis inverse matrix, right? What is the CB? Currently, the basis set is 4, x4, x3, and x1. So CB becomes 0, 20, and 60, right? And we've got the new basis inverse matrix right here, right? Then it becomes 0, 10, 10, okay? Now we need to price out the non-basic variables, which means compute the reduced cost or the relative profit of each non-basic variable. Currently, the non-basic variables are the x2, x5, and x6. So first, not the reduced cost, because this is the maximization problem. The relative profit for x2 variable is computed by this formula, right? And C2 is 30, right? Minus pi, which is this, 0, 10, 10. And what is A superscript 2? That is the constraint coefficient corresponding to the x2 variable, which is 6 to 1.5. And this is negative 5. Okay? What about the reduced cost for x5 variable? C5 minus pi times A5. What is C5? 0 minus pi, 0, 10, 10. And A5 is the constraint coefficient relative to x5 variable, which is 0, 1, 0. And this value becomes negative 10. And lastly, the relative profit for x6 variable is C6 is again 0 minus simplex multiplier vector times constraint coefficient for a x6 variable, which is 0, 0, 1. And this value is again negative 10. So what is your conclusion? Because every non-basic variable has a non-positive coefficient in the objective function rho. So this is the optimal. Okay? And to find the optimal solution, we need to get the right-hand side values, right? Which is xb is x4, 3, x1, right? Which can be obtained by basis inverse matrix times the right-hand side value from the original table. Okay? And this is going to be 1, 0, 0, 2, 2, negative 0.5, negative 8, negative 4, 1.5. And the right-hand side value from the original table is 48, 28, right? And this value becomes 24, A2, which means our optimal solution is x4 equals 24, x3 equals 8, x1 equals 2. And the corresponding objective function value g can be obtained by CB, AB inverse, and B. Okay? The CB is again 0. What is that? That's 0, 10, 10. How come I have 0, 10? The current basis is 4, x4, x3, x1, right? So 0, 20, and 60 times this value, 24, A2, right? This must be 280, okay? Any questions about this example? Okay, so if you don't have any questions, let's move on to another example problem. So at this time, let's deal with minimization problem instead of maximization problem. Okay? Okay, so in this minimization problem, first of all, we need to standardize this given problem, right? So we need to introduce slack variable, let's say x4 for the first constraint, and surplus variable for the second constraint, let's say is x5. Okay? However, in this case, although the x4 variable, which is the slack variable in the first constraint, that x4 variable can be used as a basic variable in the first row. However, the choice of a basic variable in the second constraint is not obvious, right? So we need to introduce an artificial variable, and it will be used as a basic variable in the second row, right? So this LP can be rewritten as this. For x1, 8x2 minus x3 plus x4 becomes 5. 7 x1 minus 2x2, 2x3 minus x5 equals 4, right? And we need to add the artificial variable, right? And all the variables x of i's are greater than or equal to 0 for all I equal to 5, equal to 1 through 5, right? And let's just suppose we've used two-phase method to solve this problem, and the phase 1 has found the initial basis, okay? Which is 1 and 2. Okay? Then what does this mean? Initial basis is 1 and 2. The first element is the basic variable in the first constraint, right? Which means x1 variable is the basic variable in the first constraint. Likewise, the second element of B is the second basic variable, right, in the second constraint. Which means x2 variable is the basic variable in the second constraint. So now we can begin the first iteration of phase 2. Okay? And this is the initial tableau constructed based on this standardized LP. Okay? And I've mentioned the phase 1 found the initial basic variables, which is x1, and x2, right? And the basis set B equals 1, 2 tells us the basic matrix, which is represented by A superscript B is 4, 7, and 8, negative 2. Is that right? Because the basic variables, columns of the constraint coefficient matrix, which is this part, right, is the basis matrix. Okay? And we've learned the basis inverse matrix can be obtained easily by updating the old basis inverse matrix. But in that case, the old basis inverse matrix is not available, right? And actually, for 2 by 2 matrix like this, for example, A matrix is A, B, C, D. Then the A inverse matrix can be obtained by the formula 1 over AD minus BC and DA negative B and negative C, right? Or by using the Gauss-Jordan elimination method, you may obtain inverse of this matrix. Okay? So, new basis inverse matrix is 0.031 to 5, 0.10937, 0.125, negative 0.026, 0.625, sorry. Okay. Okay, so again, we have the initial tableau and the basis set and the basis inverse matrix, right? So we are able to begin the first iteration of phase 2. The first step is to compute the simplex multiplier vector, right? Which is pi right? What is the value of CD? That is 3 and 2, right? The basis inverse matrix here. Then the simplex multiplier vector becomes 0.3125 and 0.25. Okay? Next step is to compute the reduced cost of the non-basic variable, because we are dealing with minimization problem, right? And Currently, the basic variable is x1, x2, which means we have 3 non-basic variables, x3, x4, and x5, right? So let's start with x3 variable. Pricing x3. The reduced cost is C3 minus pi times A3, right? What is C3? That is the objective coefficient for x3 variable. So 6 minus pi 0.3125.25. What is A3? That is the constraint coefficient corresponding to x3 variable, which is negative 1, 2. And this value is 5.1875, which is positive. Because the reduced cost is positive, increasing this x3 variable would increase the cost, right? Which is the objective function value. So x3 variable should be rejected as a pivot variable, right? Now we proceed to the next non-basic variable, which is x4, right? The reduced cost can be obtained by same type of formula. This should be 4, right? What is C4? That is 0, right? Minus pi 0.3125.25. What is A4? That is 1, 2, right? 1, 0. And this value is negative 0.3125. Okay? So increasing this x4 variable will improve, which means lower the objective function value, right? And because its reduced cost is negative, right? So rather than continuing to price the remaining non-basic variable, we can just proceed by entering x4 variable into the basis, okay? To save the time and effort, okay? So next is step number 3. So this is the current table, and x4 variable has been chosen to enter the basis, right? And the reduced cost for x4 variable is negative 0.3125, right? Next, you need to determine the leading variable by performing the minimum ratio test, right? So we need to get this value, which is called the substitution rate, right? And also we need to know the right-hand side values for the current table. First, the substitution rate, alpha, can be obtained by basis inverse matrix times constraint coefficient, corresponding to this entering variable, right? So we have basis inverse matrix right here. And what is A4? A4 is 1, 0. Right? And I've got the values, which is 0.03125, 0.10937. Okay? So we can add this value to the current table, which is 0.03125 and 0.10937. Okay? And the right-hand side value, which is beta, can be obtained by basis inverse matrix times the right-hand side value from the original table, right? So we have basis inverse matrix right here. The right-hand side value from the original table is 5, 4, right? And I've got this value, which is 0.65625, 0.296875. Okay? So we can add this value to the current table. 0.65625, 0.296875. Okay? Now you are able to do the minimum ratio test. So the minimum ratio test is 0.65625 over 0.03125 and 0.296875 over 0.10937. Okay? And this value is approximately 21, and second value is 2.71. Okay? So minimum occurs at the second row. And because the second row is minimum, the second basic variable, which is x2 variable, is replaced by the entering variable, which is x4, right? Which means the new basis P becomes 1, 4. Okay? And the new basis is 1, 4. This tells us the basis matrix A superscript B is 4, 7 and 1, 0. Right? I said the basis matrix can be obtained by taking the basic variable columns, which is x1 column and x4 columns of the constraint coefficient matrix, right? Now we need to update the basis inverse matrix, either by using the formula or by using Gauss-Jordan method. Okay, whatever you feel convenient. And from this, the new basis inverse matrix is 0, 1, 0.1428, 0.57, negative 0.571429. Okay? So, right now, again, we have initial table and new basis set, which is 1, 4. New basis inverse matrix, right? Which means we can begin another iteration of the revised simplex method. Okay? So, iteration number 2 of phase 2, right? And again, the first step is to compute the simplex multiplier vector, which is pi. And CB is 3, 0, right? And the basis inverse matrix right here, then pi becomes 0, 0.428571. Okay? And step number 2 is to compute the reduced cost of the non-basic variables. Currently, the non-basic variables are the x2, x3, and x5, right? First, the reduced cost for x2 variable is C2 is 2, right? Minus pi value, which is this, right? What is A2? That is the constraint coefficient correspond to x2 variable, which is 8, negative 2. This value is 2.86. Okay? Next, reduced cost for x3 variable. C3 is 6 minus pi times A3 is negative 1, 2. And this value becomes 5.14. And the third non-basic variable, x5, the reduced cost becomes C5 minus pi times A5. C5 is 0 minus pi times A5 is 0, negative 1, right? And this value is 0.43, okay, approximately. And because the non-basic variables, every non-basic variable has non-negative reduced cost, which means the current basic solution is optimal. Okay? Again, the optimal solution can be obtained by basis inverse matrix times the right-hand side value from the original table. Okay? And the corresponding objective function values can be obtained by CB, AB inverse B. Okay? Any questions so far? Okay, then now I'd like to introduce another theorem in duality, which is related to simplex multiplier vector. So like this screen says, if the basis set is an optimal basis of the primal problem, then the simplex multiplier vector pi relative to this optimal basis is an optimal solution to the dual problem. Is that complicated? Then let's consider an LP maximization problem. So this LP problem has 2 variables and 4 constraints, right? So its dual must have 4 variables and 2 constraints, right? Let's make the dual problem together. So dual problem must be minimization problem, right? Let's say the objective function is W. And the right-hand side values of the primal problem serves as the objective coefficient, right? So 8, y1, 18, y2, 15, y3, 10, y4. Okay? And the transpose of the constraint coefficient becomes the constraint coefficient in the dual problem, right? So 1, 3, 2, 5, 1, 2, 5, negative 1. Okay? y1, 2, y3, y4. And the objective coefficient in the primal problem becomes the right-hand side value, the dual problem. So we have 4 and 5. Okay? And because this is the dual in the symmetric primal dual pair, so the minimization problem must be greater than equal constraint, and all the dual variable should be greater than equal to 0. Okay, so this is the dual problem. And this is the optimal simplex table for the dual problem. Okay? Suppose I've just run this dual problem using Lindo, and I've got this optimal table for the dual problem. Okay? So the optimal solution to the dual problem is y4 equals 14 over 27, right? And y3 is 19 over 27. And all other variables, likewise, y1, y2, and s1, s2, all of them must be equal to 0, right? The corresponding objective function value I think should be w instead of z, right? Is 505 over 27, right? From this optimal table. Then let me ask you a question. What is the optimal solution of the primal problem? The optimal solution of primal problem. The primal variables, so x of i's, right? So x1 is 65 over 27, x2 is 55 over 27. How do I know this? I will show you in a minute with the simplex multiplier vector. Pi is this value, okay, which is 65 over 27, 55 over 27, okay? Because just ago, in duality theorem, says the simplex multiplier vector pi provides the optimal solution in the other problem, in the symmetric primal dual pair. Okay? And the pi value becomes this because the reduced cost of the surplus variable. In our case, we have two surplus variables, S1 and S2. Okay? The reduced cost for the first surplus variable, S1, is cost minus simplex multiplier vector times a superscript S1. That is the coefficient, constraint coefficients corresponding to S1 variable, right? So what is this? C sub S1 is 65 over 27, right? Minus pi times a superscript Si, which is these values, right? Oh, I'm sorry. I should not use the optimal table to compute this. What is the initial table? Okay, I didn't make the initial table, right? Actually, I've got the dual problem. So first of all, we need to standardize this, right? Just 8y1, 18y2, 15y3, 10y4. Subtract 2, y1, 3y2, 2y3, 5y4, y1, 2y2, 5y3 minus y4. And negative s1, negative s2 equals 5 and 4, right? And all the y variables are greater than or equal to 0, and the surplus variables are greater than or equal to 0, right? Sorry about this. Okay, so now we can construct the initial table based on this standardized LP, right? So the initial table for dual problem is negative W, Y1, Y2, Y3, Y4, S1, S2, right hand side. Is that right? Eight, 18, 15, 10, 0, 0, 0, 1, 0, 0, 1, 1, 3, 2, 2, 5, 5, negative 1, negative 1, 0, 0, negative 1, and 4, 5. Is that right? So this is the initial table for the dual problem. And I said the simplex multiplier vector for S1 variable can be obtained by C sub S1 minus pi times A S1, right? So C sub S1 is 0. Is that right? 0 minus pi times, what is this value? A superscript S1. There is the constraint coefficient for S1 variable, right? Negative 1, 0. So this value becomes pi 1. Okay? Because this negative, negative becomes positive, right? Likewise, the reduced cost of the surplus variable for second constraint is C sub S2 minus pi times A superscript S2. What is C sub S2? There is again 0, right? Here. Minus pi times A superscript S2. That is the constraint coefficient for S2 variable, which is 0, negative 1, right? And this becomes pi 2. Okay? So if there is a surplus variable in row number I, for example, then its reduced cost becomes just pi value. Okay? And here the duality theorem says the simplex multiplier vector pi provides the optimal solution to the other problem in symmetric primal dual pair. Okay? So the optimal solution of the original primal problem becomes the pi value, which is this in the optimal table. Okay? Because these are the reduced cost for S1 variable and S2 variable. Those are the two surplus variables, right? So, in summary, the reduced cost for surplus variable provides the simplex multiplier vector, okay, which becomes the optimal solution in the other problem, in symmetric primal dual pair. Okay? So once you solve the dual problem in this case, then you don't need to solve the primal problem. Okay? Because this final optimal table provides the optimal solution for the primal problem automatically, like this. Okay? So we may choose to solve either the primal or the dual problem, whichever is easier, and then obtain the solution to both simultaneously. Okay? And if you compare these two problems, this primal problem and the dual problem, this dual problem has fewer constraints, right? It has only 2 constraints. But the primal problem has 4 constraints, right? So when you solve this problem by the simplex method, the dual problem requires fewer computations per iterations, especially if you want to use the revised simplex method. Because many LP computer programming code does use the revised simplex method. And in the revised simplex method, if you know the initial table with basis inverse matrix, you are able to compute all the other part of the current table, right? So the computational effort in the revised simplex method highly dependent upon the size of basis inverse matrix, okay? Which means the computational effort required to solve an LP will depend primarily on the number of constraints, not the number of variables, okay? So suppose you are required to solve an LP, primary LP, with, for example, 99 constraints and maybe only 5 variables, okay? Then in that case, each basis inverse matrix will be 99 by 99 matrix. Is that right? And in this case, this LP dual have only 5 constraints, but 99 variables, okay? Then all the basis inverse matrices for the dual problem will be 5 by 5 matrix, okay? So which one do you want to solve in that case? it will be much easier to solve the dual problem than to solve the primal problem if you want to use the revised simplex method. Okay? Okay, then let's go back to our example problem. I need to look for put it. Okay, I think this one. Sorry, I cannot find the problem set. Okay. Okay, I've got the dual problem, but I cannot locate the primal problem. Okay, let me just write it down here. Our primal problem was minimize 3x1, 2x2, 6x3. Subject to 4x1, 8x2 minus x3 less than equals 5, 7x1, 2x2, 2x3 greater than equal to 4, right? And all three variables, x1, x2, x3 is greater than equal to 0. This is the primal problem, and we've already solved the primal problem, right? And then the dual problem would be maximization problem, right? And it's going to be 3 by 2. So W is 5y1, 4y2, 4, 7, 8, negative 2, negative 1, 2. Right? And 3 to 6, all the dual variables are greater than equal to 0. And all the constraints should be like this. Or no, y1 variable should be less than equal to 0. Instead of greater than equal to 0. But y2 is greater than equal to 0, right? Okay, now, again, let me ask you a question. What is the optimal solution to the dual problem? We didn't solve the dual problem, but we've got the optimal solution for the primal problem already. If you look at the pi values, the last iteration, pi is this, right? pi value is 0.428571, right? What does it mean? This pi value provides the optimal solution in the other problem, which is dual problem, right? So this 0 is y1, and 0.428571 should be y2 value, okay? And with this value, y1 and y2, you can get the optimal objective function value in dual problem too, which is 5 times 0 plus 4 times this value, 0.428571, which must be 1.714284. And this must be exactly the same as objective function value in the primal problem. Okay? Any questions? Okay, then I'm going to stop here for today. And next time, I will give you another example for revised simplex method. But the next time, I will try to give you the whole procedure for the implementation of revised simplex methods for two-phase methods. Okay? So it's going to be a little bit complicated than the regular problem. Okay? Okay, thank you. I will see you next time. Bye-bye.